welcome everybody. We are very pleased to have Sandipan Kundu. So Sandipan did his PhD in with Willy Fischler in Texas A&M, and he did a postdoc in Cornell, and now he's a long-term postdoc in Johns Hopkins. And Sandipan is a frequent visitor to India, so I think many of you know him. And he's going to tell us about quantum field in a box. So now it's up to you, Sandipan.
Thanks, Anindo. Thanks for the invitation. So this talk is based on this paper of mine that came out a few months back. So before I actually begin, let me mention that please interrupt me whenever you have any question, comments, or whenever something is not clear. Please don't hesitate. Before I actually begin, let me do one thing. Let me state the main 2 points that I'm going to focus throughout these lectures. So basically the slogans are, these are the slogans. So there are effective field theories. For some reason, it's not, okay, there is a lag, okay. That cannot be embedded into UV complete theories. So this is the first point that I'm going to focus on. And the second point is the space of consistent effective field theories can be analyzed in a conceptually clean way by putting the EFT in anti-de Sitter spacetime, which is practically a box because of the gravitational potential. So basically, these are the 2 points that I'm going to focus on, and the goal of this talk is to explain these 2 points in some details. So conceptually speaking, effective field theory in a box, because ADS behaves like a box, effective field theory in ADS is, morally speaking, analogous to something like a quantum particle in a box, which we know and love. So this is the main idea. So now let me give you the outline. I think, yeah, I don't think it's responding. Let's see. Yeah, I don't know why there is a lag actually. Okay. So today I'm going to discuss the general setup. So which include some discussion about effective field theories in ADS and their CFT duals. Then in in the next lecture, I'll discuss a very specific CFT theorem, which is particularly useful for this kind of CFTs that are dual to effective field theories in ADS. And in third lecture, I'm going to put everything together to derive bounds on scalar effective field theories. So this is the outline for this lecture series.
Sandipan, while your iPad catches up, can I ask you a precise definition of how you're going to test whether something is UV complete or not? I mean, are you going to use dispersion relations or something else? I mean, how do you check that something is not UV complete? Okay,
yeah, that's a very good question. Actually, there are two answers. So for example, first, in flat space, basically what all I'm going to assume is that the full amplitude, like or the amplitude of the full UV complete theory, at low energy, it coincides with the effective field theory amplitude. But when the energy is high, it's basically always the standard unitarity, crossing symmetry, those kind of conditions. But today, what I'll do is basically I'll translate that question into a CFT question, which is basically the statement that the effective field theory can be embedded into a UV complete theory, which has a CFT dual that obeys all the Bootstrap axioms.
I see. Yeah, but suppose I give you the low energy amplitude or then unless and until you use some extra property, something like a dispersion relation, something like how the high energy behavior looks like, or I mean, unless and until you're doing some perturbative unitarity checks, that's a different thing. So, but how will you tell me whether that is UV complete or not, or that can be embedded?
Okay.
Yeah.
So basically, yeah, it's basically I'm going to derive a dispersion relation, which follows from like this unitarity, this kind of conditions. So basically, yeah. So that's so that dispersion relation is basically okay. One can start with this dispersion relations, or one can start with this set of axioms and derive the dispersion relation. Yeah, that's the main idea.
Okay. Okay.
Now, obviously, you can ask like whether the assumptions are valid or not. That's a separate question, and that's kind of the reason why I'm discussing the CFT part.
Right.
Okay. So, so let me now begin with today's lecture. So, whenever we think about effective field theories, the picture that we have in mind is the following. So we have some UV complete theory. Then we integrate out some heavy fields, and we recover some effective field theory at low energies. So that's the standard picture. The traditional wisdom says that whatever interaction is any interaction which is consistent with all the symmetries of the system is allowed in effective field theory. However, that's not completely true. So the important point is that like a conceptual shift took place in 2006 from this traditional understanding of effective field theories. So what happened in 2006 is the following. There was a wonderful paper from Addons, Arkani Hamed, Wasky, Nicolis, and so basically what they showed is the following. They showed that there are IR effective field theories that look completely normal, but they can never be UV completed. So that's a really important step towards the concept of basically like there are IR obstruction to UV completion. So this is something I'm going to explain today. But before I do that, just for warm up, let me discuss another different example. So for warm up, let's consider the following theory. So I have a scalar field phi, which is massless, and there is another massive scalar field psi, with some 3-point interaction between phi and psi. So in this theory, let's consider a 2-to-2 scattering of phi phi goes to phi phi at tree level. So the low energy amplitude, or the full amplitude in this case, is basically given by the following Feynman diagram plus other channels. So we can actually compute this amplitude. Now what we want to do is take the limit for the Mandelstam variables. They are much smaller than m squared. So if I expand at for small energies, I'll get the following result. Now I can write down an effective field theory action only for the phi field. So at low energy, this theory can be equivalently described by the following effective action. Where this mu is an IR coupling constant, which is basically given by some positive number times lambda square, where lambda is the coupling constant for the original theory.
Sandipan, if you want to take low energy, why do you also have to take T less than m square? Just S less than m square is not good enough.
You have to take all the energy. Basically, energies in all channels should be small, not just the S channel.
I see. Energies in the all channels to be solved.
Because like this is just a single exchange diagram. You have all the other channels as well, right?
Right. I see. Okay.
And also like basically like also like S plus T plus U is also 0. So basically the that basically like you cannot have one of them large but other two small. That cannot happen anyway.
I see. So let me answer. Suppose I made the phi's to be colored, let's say, or say some index ij index. Then the different channel will have different, the color structure or those other structure.
Yeah.
Then I can just restrict myself to one channel and take just only one of them to be less, and then will still this work.
In that case, basically, like you always have to take all the energies to be small, but in that case, basically, what will happen, basically, like other limits will not matter. Or like taking S to 0 will actually do the trick. So basically, what you're saying in that case, this S square plus T square plus U square will not be there. You'll have like something like just S square or like some different coefficients for each terms.
Right.
Yeah, but like just to expand. So since we're trying to write down a low energy effective theory, so basically all the energy scale should be small.
Okay.
It's basically the way to think about it is basically like you can look at this amplitude in either complex S plane, complex T plane, or complex U plane. So basically, when I say small energy, it's basically you are not actually crossing the pole because of m square in this case.
Okay, thank you.
Okay, so now the important point is, so this mu is proportional to lambda square and the proportionality constant is positive. So this mu coupling constant over here, it's actually positive for this particular example. Now one can ask if this is true in general. At first sight, this question seems to be very, it seems to be a very difficult question, because obviously a priori it should depend on what kind of theory you start with in the UV, and then when you integrate out heavy stuff, you get a low energy effective field theory, and that will depend on what high energy theory you started with. So at first sight, it may look like this is a question that's very difficult to answer. There is actually a similar question that one can ask. Let me mention that here as well. So there are other higher derivative terms that's there in this effective action. So I can try to write down the other terms as well. So let me write it in the following way. Let me write it again. So the interaction part looks like this, at least for this particular case. Plus a constant times m square. So the higher order interactions have this particular form. So there are coefficients C1 and C2. All of them are order 1 for this particular example. And as you can see, as you increase the number of derivatives, you get higher powers of 1 over m. Where m is in this case, m is the mass of the particle that was exchanged. So now, obviously, this fact depends on the UV theory we started with. So again, one can ask if this is true in general. If this fact that all coefficients such as C1 and C2, they should be order 1, and all higher order interactions should be suppressed by higher powers of the cutoff scale, is that a true statement? So that's something that I'm going to discuss next.
And
so this brings us to
sorry, there is no restriction on the sign of the C1s or anything, right? It just,
oh yeah, that's a very good point. Yeah, thank you. So actually, for this particular case, you can actually check that. Let's see. For this particular case, actually, you can check that there is the C2 is positive as well. C1, I don't remember now, but in general, like this, the fact that C2 is positive, it's actually a general statement, true statement in general. I don't remember the value of C1 for this particular example, but for C1 in general doesn't have to be positive.
I see. Okay.
Okay, this brings us to the Addons et al. Paper. So this is the paper from 2006. Okay, so this is what we want to do. So we now start with the effective, the scalar effective field theory to begin with. So I don't care how I get this effective action. I just write down an effective field theory with a single scalar field with higher derivative interactions. So for these dots can include any other interactions that are present. For example, there can be higher derivative interactions, but the goal is to study this effective field theory by itself without really caring about how we get this effective field theory. And there is a way to do that. First of all, again, I can write down the low energy amplitude. So again, this is valid for energies much smaller than some cutoff scale, which is but since we don't know the exact UV theory, we don't know anything about this cutoff scale, but we know that there is a cutoff scale in the theory, because otherwise this effective field theory is not valid up to some large energy scale. So as you can see that this term is, even the tree level amplitude is growing with energy. Okay, the next step is basically okay, before I proceed, the way to think about this amplitude is the following. You should think about this amplitude as an approximation to some full amplitude. So basically this full amplitude is well behaved even when energy is very large, but at low energies this gives you this low energy amplitude. So we don't know anything about, we don't know the exact full amplitude in this case. Only thing that we know is that at low energies, it coincides with the low energy amplitude of the effective field theory, which is this answer over here. Now we can make the following assumptions. About the full amplitude. First of all, it's analytic. In exactly the regime of analyticity I'll discuss in a minute. The second condition is this is crossing symmetric. Then unitarity. And Reggie boundedness. So basically, what the main argument is the following: even though we don't know the full amplitude, we are going to assume that it has the standard fit. Basically, the amplitude is well behaved even when we take the energy to be large. So, and the definition of well behaved in this case is basically the amplitude is analytic, crossing symmetric, unitary, and Reggie bounded. However, I have to make one comment over here. There is no rigorous proof of this set of assumptions, but they are believed to be true from our experience with quantum field theory for probably 70-80 years now. So these assumptions.
Sandipan, why so far as crossing symmetry is concerned, for massive external scalar scattering, 2-to-2 scattering, I thought crossing symmetry was proved by Bose-Epstein-Glaser. So is there a reason why you feel that that is not rigorous?
Even for like the 2-to-2 scattering amplitude, I think it's not. I think I don't think that proof is for all external states, is it?
No, for massive external states.
Yeah, so for massive, I can, yeah. But in this case, in this particular case, phi is massless.
Ah, I see. Okay, in that sense, fine. Yeah.
Yeah, but yeah, in fact, like when external states are massless, actually, as I was saying in the beginning, there is some discrete difference between massive and massless states. So yeah, that point can be important at the end.
Right. Okay.
So
here,
in fact,
yeah.
Yes.
So here actually, I mean, when you're considering there to be a cutoff, then and if the cutoff is much bigger than any other scale in the theory, for practical purposes, you can consider the theory to be massless. But you're making a distinction that a strict masslessness from approximate masslessness.
Yes, that's right. That's right. So in this case, it's exactly massless.
Okay.
And that assumption is, I don't think that's necessary. I think that's kind of a simplification. I think I can make the same argument without even assuming that it's massless, but like that yeah, that's a different
okay
example. And also, I guess the most problematic assumption among all this is this Reggie boundedness assumption. The reason is this assumption is basically the statement that the forward amplitude for large S is bounded by a square. Even though this is this follows from facade bound when there are no massless state in the theory, but whenever you have massless states, there is no reason to believe that this is true in general. So this does not follow from facade bound when there are massless states. For example, even if you are considering, let's say, an effective field theory of Goldstone modes, Goldstone modes are massless. So in that case, you have to have some other argument to justify that this boundedness condition is valid. Otherwise, this is an assumption.
Are you going to elaborate on this? Because I mean, I've seen this is confusing at many levels, but I've seen people use the fact that there is a chaos bound and that translates into something similar. And many people claim that is rigorous. So can you elaborate on this?
That's like there are statements similar to that. That's rigorous. For example, what can be shown rigorously is the following fact. So if you have some effective field theory that violates this Reggie boundedness condition, then if you take that effective field theory and put it in ADS and study the chaos bound in the dual CFT, then you can show that like this, the same effective field theory also violates the chaos bound. But if you want to map one-to-one, that like this Reggie boundedness condition follows directly from chaos bound, just from a like rigorous analysis, that's more I think that's harder. I don't like the examples that I know of, either they are like special cases or they are like external states that are scalars, things like that. Like in general, I don't think there is a rigorous proof.
Okay. And another thing that I want, great. Thanks for the clarification. And another thing that I wanted to clarify was that you have put less than s squared, so that literally means that it is like s to the power 2 minus epsilon.
Exactly. Yeah, that's very important. That's like this. Like if it's s squared, then there is no proof of like everything I'm going to say next that will break down.
Okay, thank you.
And actually, that's very important. Like I'll come back to that. Okay. Oh, by the way, what's the time situation?
You have till 12 o'clock. So we started a bit late, so you can finish at 12:05, 12:10.
Okay. Okay.
Yeah.
Let me now give you a brief sketch of the proof that. So, okay, before I proceed, the goal is to actually prove that this mu is positive, just from these assumptions. The way to do that is basically, let's consider the complex S-plane. So the full amplitude, it is analytic everywhere on the upper half plane, but it can have non-analyticity on the real line. So from, let's say, s equals to s naught, s equals to minus s naught, and it is analytic everywhere else. So that's the analyticity assumption that I made in the last page. Now I'm going to consider this contour integral. Where the contour is the following.
Sorry, just to understand, you will allow for poles other than those are allowed. Those are allowed.
Yeah, poles and branch cuts, they're allowed. Yes.
So branch cuts are only branch cuts allowed. Are this s is equal to s naught? These are the only branch cut allowed.
Yeah. So basically, like when I say basically all the non-analyticity, they are above s equals to s naught. So okay. There can be like multiple poles and branch cuts, but everything is basically above s equals to s naught.
I see. Just one second. I have a question to Aninda. Aninda was explaining once that there can be poles which may go away when I do in the amplitude. There can be poles, but AA dagger may not have pole because the A dagger might have a pole, whereas A can have a 0 and they cancel out. Am I remembering correctly? Sorry.
So that's a resonance.
That's a resonance.
That is a statement about resonance, which is in the complex, which moves away from the real axis. The statement is that it is a pole in the unphysical sheet. So it's a 0 in the physical sheet, but a pole in the unphysical sheet.
I see.
And analyticity, when we talk about analyticity, are those taken also into account, or those are not taken into account?
So the amplitude is supposed to be analytic in the blank space that Sandipan has drawn. So that is the assumption that it is supposed to be. There is nothing else.
Nothing else, right?
So there are no. Yeah. So there are no poles away from the real axis. For example.
I see. I see. So the resonance you said that is not in this. That's in another set. That's what you're saying, right?
Yeah. That is in the unphysical sheet. Yeah.
Okay. Okay. Thank you.
Yeah, that's an important point. Yeah.
Hi, Sandipan, I have a question.
Yes.
So what about loops coming from this massless external particle exchanged in between?
Massless, you mean like the particle itself?
Yeah, if that is exchanged in between, you'll have massless loops.
Okay, yeah, that's a good point. So basically, like when I say this S0 actually in principle can go very close to the origin. So that's allowed. So basically, the way you should think of like this S0 is basically something like an IR cutoff. So the reason I'm using S0 and it's not 0 is the following. So because of this contour integral, there is also a pole here because of this 1 over S cube. So I'm basically separating that pole from the poles or branch cuts that's already there in the amplitude. And this S0 basically plays the role of the regularization. So basically at the end of the computation, you can just, sorry. Okay. So at the end of the computation, you can take the limit S0 to 0. And that will basically include like all the branch cuts that you're talking about, but it's just a regularization process. It's not going to change the result.
Okay, thanks.
And
what will happen to the low energy cuts?
Say that again.
What will happen to the low energy cuts? This is a massless theory, right?
Yeah, so basically the low energy cuts, they will be there and they will extend up to S equals to 0. But as I said before, like this S0 is basically playing the role of a regulator. So I'm not taking the branch cuts to 0 to begin with. I take them, I place them at some finite S0, and they can take the limit that it's approaching limit.
Okay.
Or so this is basically just a way to derive the dispersion relation. You can actually derive it in different ways. For example, if you want to be very precise, what you can do, you can use a different contour. So what you can do, you can take a semicircle on the upper half plane, you can take another semicircle on the lower half plane, and then derive the dispersion relation using that entire contour. So that's more precise in the sense that does not pass the real axis at all. And you can derive the same dispersion relation from that contour as well. But at the end of the day, you'll see that you'll get the same dispersion relation. Like it's not that there is any correction when you take S0 to 0.
Hi, Sandipan. Just
Yes,
one question
yes.
about this two semicircles.
Yeah.
If you have a branch cut on the whole entire line, then how do you make comparisons of what is above there's no analytic way to continue? How do you make the statement that the amplitude above and the amplitude below the cut are related by this real analyticity or something?
It's basically in that case, like the amplitude on the lower half plane is defined by source reflection. That's always well defined. So all I'm saying in that case, you can use the following. Let me draw a different contour. So in that case, you can use the following contour. So in that case, basically, you don't cross the real axis at all. So you have this upper semicircle, you have this lower semicircle, and then you can derive the dispersion relation from that contour. So you'll get basically two different expression from the upper half plane, like so we cycle on the upper half plane and from the lower half plane, and then you can just rearrange them and you get the same dispersion relation.
I was just making the statement that whatever AS plus I epsilon and AS minus I epsilon are usually related by this real analyticity. That AS plus I epsilon is A star S minus I epsilon. Right? Real analyticity follows only if there is a real region in which it is true, which is true only if you have a if you actually don't have a, there's some gap, there's no cut. If
But
you don't have a gap, this statement that real analyticity of the amplitude follows, this doesn't, at least I don't know how it follows them. I mean, how do you
actually the on the lower, like the statement is that, so if you define the amplitude on the upper half plane, by definition the amplitude on the lower half plane is defined by source reflection. So it's kind of by definition that's true.
Okay, I see.
So it's not a derivation, it's a definition.
Sandipan, isn't Schwarz reflection applicable only if there is some part of the real line on which the function is defined?
Yeah, that's what I meant. It's only applicable when you have when there is a real region in which this holds. There has to be a real region in which it holds, and then you can analytically continue to the whole complex.
Oh, yeah, but you have to remember one thing. So it's kind of that statement holds because of the following reason. So it's basically a statement. It's basically a perturbative statement. If you take the tree level amplitude, there is no analyticity anywhere on the real axis. So basically, just from the tree level amplitude, you can define the amplitude is well defined on the real line. So the non-analyticity shows up only when you go to higher. Basically, only when you go to the loop order. So in that sense, so if you define the amplitude order by order in the perturbation theory, in some sense, amplitude is still defined on the real axis. For example, it's given by this expression, which does not have any non-analyticity. So roughly, as I said before, this analyticity condition, it's an assumption. So the assumption is the following: is basically it's analytic on the upper half plane, and on the lower half plane, it's always the source reflection of the upper half plane. So you can take that as an assumption of this derivation. Now the question is, like the important question is if that assumption is true or not. That's a different issue, and I'm going to discuss that. Is that answer your question?
Yeah, thanks.
Sorry, can I ask another question?
Yes, yeah.
So when you're allowing these low energy loops, are your Wilson coefficients, your Wilson coefficients are supposed to get renormalized, right? They'll run. So
Yeah, that's
are
right.
the statements you're making going to be for those, or do you assume they don't run and then it's about those Wilson coefficients?
That's a good question. So basically, the statement that I'm going to make about, there are many statements that you can make. The statements that I'm going to make about this particular Wilson coefficient on the running. But you may derive similar conditions for high derivative interactions with like more than 4 derivatives. And then you have to be careful about the statements, because those statements can include loop effects. So depending on what kind of bounds you're deriving, it will, the fact that you're including loops or not, that will matter.
Right. The reason I'm asking is, for example, in the EFT hedron sort of story, you have to redefine these couplings by moving the pole to the imaginary axis. Before you talk about those then. You don't have to do any such thing, right? I mean, directly.
No.
Okay, thanks.
Okay, so let me erase this. Okay, so from this contour, I get the following expression. So I have an expression for mu in terms of this contour integral. The Reggie boundedness condition, as I mentioned before, what it does is the following. It tells us that the contribution from infinity, that's these two loops, they drop out. So from here, you can write down a dispersion relation of mu, which goes as follows. So this is like this. This follows from the contour integral plus crossing symmetry. And obviously, the Reggie boundedness condition was also assumed. So since we are discussing this before, note that the imaginary part of the amplitude, it's 0 for when S is 0. At least from the tree level amplitude. So that's why it's okay to take S0 to be non-zero to begin with, then take the limit that S0 goes to 0, because this amplitude at the tree level vanishes. Now, the next important thing is you can write imaginary part of the amplitude, the forward amplitude, just from optical theorem. You can write that as S times sigma S, where this is the total cross section or phi scattering. So that means basically the imaginary part of the amplitude, this is strictly positive. So even though we don't know the full amplitude, we know the integrand is strictly positive. So that's why mu is strictly positive. So that's the argument of Addons et al.
And I did not get the first statement. A full by S cube is equal to 16 pi I pi mu. How do you get that? Sorry.
Oh, that's because so this quantity has a pole at 0. So and otherwise this contour.
So how do you know A full? It just you just wrote down the tree level thing like S square plus T square.
Yes. So basically the A full is something that we don't know. The only thing that we know that the full theory, the effective field theory comes from some equicomplete theory. A full is the full amplitude in that theory. But I don't actually need to know the full amplitude. Since the contribution from the pole, that basically a low energy effect, you can just use the EFT to compute the right hand side.
Oh, I see. In the S goes to 0 limit, you will get that.
Yeah. So since the pole comes from S goes to 0 limit, that's where the effective field theory description is valid. So I know so this is a very nice result in that sense. In the left hand side, I have something which is completely IR. And on the right hand side, I have something which is completely, which includes UV.
Not only IR, it's also just the tree level, right? If I'm
yes, yeah. So even if you include like loops and other effects, but when you take the limit S goes to 0, everything will drop out. So this contour integral is designed to pick up the effective, like the tree-level effective field theory result. I see. Okay.
Sorry, Sandipan.
Yes.
There's no assumption about the EFT being weakly coupled here, because Addons et al. I thought.
No, definitely. Like I'm using perturbative analysis, so in that sense, it's weakly coupled. Obviously, yes.
So I mean, if I understand correctly, for them, for instance, loops were not allowed. They were not allowing low energy.
No, like if loops, basically these dots, they include loops.
Okay.
But when you take the forward limit of the amplitude, and basically the statement is the right hand side of this expression, this is basically the pole of the full amplitude, whatever it is, at s equals to 0.
Right.
So that even if there are loops, so this always comes from the first leading term.
Is that, I mean, is that clear? I mean, for example, if you have things like log s and so on, does
Yeah,
that?
but so even then, like you'll have like s square log s, those kind of term, right? Like it will not contribute to the residue.
I see. Okay. Thank you.
So the residue is always this leading term. So that's kind of like the magic of this argument.
Thanks.
Oh, I'm actually running. Really, yeah. I spent almost 1 hour on this. Let me make a couple of important points based on this analysis. So so under the assumptions I mentioned, what have we learned? We learned the following things. First of all, if mu is negative, the interpretation is there is no UV completion, because such a theory cannot come from a UV complete theory, as I mentioned before. You will get a contradiction. Second point is this bound where the equality is basically only for free theories. So in any interacting theory, mu cannot be even 0. So this bound is in some sense a semi-classical bound. The reason is you can actually derive it. Actually, let me give this as a homework. You can derive this bound even classically. So what you can do, you can take the theory that we studied, you take a classical solution of that theory. So you can check that this solves the equation of motion when this is a constant vector. Then we can study a linearized perturbation around this background solution and study this this del phi. And then from there you can show that causality implies, classical causality implies mu greater than 0. So in some sense, so in this particular sense, this is a semi-classical bound because you can derive it classically. Another important point is that this specific bound has a very famous application. So this bound implies the 4D A theorem. So this is something.
No, just one point, quibble that I have about the first statement that you make is that this is under the assumption that the amplitude dies off like s square minus epsilon.
Exactly.
I mean,
yes.
if you allow faster, if you allow that it goes like s cubed or something, then I think you won't be able to make such statements.
No. So yeah, that's the next point I'm going to make. So all these statements, they depend heavily on the starting assumptions. So this is important, and in fact, this is the very reason why I'm going to study this effective field theory in ADS, because it's conceptually cleaner. All the assumptions are well established. In fact, actually, there is a worse problem. So for example, one thing that obviously we want to do is to include dynamical gravity. In that case, the Regge boundedness condition is even more. I don't want to say the word problematic. It's even unclear whether it's valid or not, because even the tree level amplitude that goes as a square. So the tree level amplitude with a single graviton exchange, that's basically like that goes as like s squared over t, something like that for large s. For large s and small t. So there it is even more unclear that whether the Regge boundedness condition is valid or not. And another issue it's more of a technical problem. So when you include gravity, the forward limit is actually diverging because of the t channel, because of this pole at t equals to 0. So this whole argument breaks down when gravity is dynamical. But this is actually a technical problem, and this can actually be resolved by taking the low energy limit in a different way. If we don't take the forward limit, but if we study the amplitude in the impact parameter space, but for small impact parameter, then actually the same argument will work for it will work even when there are when there is graviton. It's basically this is the recent paper by Karen Huart et al. But in that case, you can derive bounds including gravity, but only for dimension above 4. The reason I'm mentioning all this is the following. So the important point that I want to make is that all these issues can be avoided if we study EFT in ADS with large radius.
So can I ask you a quick question, and maybe you can elaborate on the answer later on? You don't have to answer immediately. Is it true that any consistent quantum field theory in flat space necessarily has to one can think of it necessarily as arising from a larger limit of an ADS quantum field theory?
Yeah, that's a very good question. Not always. There are examples. In fact, like for simpler theories, it's actually more complicated. So if you have an effective field theory where all the interactions are non-renormalizable, that's fine, completely fine. You can just put it in ADS and it will work out. But if you have interactions that has coupling constant that scales as mass to the power some power, positive power, then those effective field theories are problematic when you put them in ADS.
I see. Yeah.
So it's kind of like theories that are easy to handle in flat space. That's problematic in ADS.
I see.
So it's basically.
And
yeah, go ahead.
Are you going to elaborate on this later on in maybe lecture 3 or something? I mean, so
if I have time, I will. But I can give you a one-line answer. Probably that will satisfy you. It's basically like, since when you put everything in ADS and study the dual CFT, all the dimensionful coupling constants, they will be multiplied by RADS to become dimensionless. So if there is a coupling constant which is which has dimension of mass positive, it will have RADS multiplied.
I see. Okay.
So basically that means like in the CFT side, basically the perturbation, like some perturbative statement will break down. Okay. Thanks. But when it's mass dimension negative, then basically it's always RADS suppressed. So that's why like it is always well behaved when you take the large RADS limit. Okay. Thanks. So, and as I said before, the way this should be thought of as is basically as EFT in a box. So because like if we are studying physics, which if we are studying only local physics, that should not actually depend on the curvature of the space-time. So whatever you derive just by studying local physics, that should be independent of RADS. So that's the main idea.
Sorry, Sandipan,
yes.
So when you say all these issues, meaning when there is a gravity is dynamical, that was one issue. What are all the issues you mean?
And the other issue is basically like these bounds, they depend heavily on the assumptions, and the assumptions are not well established. So for example, like the Reggie boundedness condition, even the like the fact that where the amplitude is analytic and not, those kind of statements are very important for the derivation of the bound, but like they are not that rigorous.
I see. And in putting in ADS, you will require no assumption. That's the point, that you require nothing.
Yes, it's basically when you when I put it in ADS. So basically, I have the dual CFT description. So even for this particular statement, this follows directly from conformal bootstrap. Meaning only input is basically the fact that there are OPs. That's it.
I see. So you require a dual CFT, then you don't require anything else.
Yeah, and the requirement that there is a dual CFT, it's not really a requirement, but because like I'm going to study everything at the level of 4-point function. At the level of 4-point function, this is basically this is well understood within the context of conformal bootstrap. It's not an assumption in that sense.
I see. I see. So one more thing, because you are going to put things into the box, what happens to the IR? You related IR to UV, etc. What happened to the IR region? I understand at the high energy it is not going to matter, but what happens to IR?
Okay, so now what I mean by IR is more complicated. So basically, since there is the RADS scale, so there is UV is obviously well defined. Then there is a energy scale or length scale, which is basically smaller than RADS, but like not that large. So basically, like as long as my energy scale times R ADS is large. So nothing will depend on R ADS. So the IR scale is defined such that like the energy is small, but this quantity is still large.
I see. And so, from the effective field theory perspective, as there was a discussion earlier, I cannot talk about massless fields, right? I need to talk about at least there has to be a little mass to the fields, right?
So in the argument that I mentioned before, yeah. So they are basically like, even if you have massless fields, then basically everything, like either you have to take everything massive and then take the massless limit, or basically you have to just assume that all the assumptions are valid.
Okay.
So now I guess the problematic thing is then you have to argue whether those assumptions are valid or not. But here in ADS, actually I don't actually care about like if I just look at the assumptions, they are always like, they are basically just a statement that in CFT we have OPs, that's it.
Okay. Okay.
I had a question.
Yes.
So when you study these EFTs in ADS, there are no branch cuts, is that right?
Branch cuts in what? Amplitude or?
Yeah, I mean, so like, for example, when you take the large radius limit and try to connect this to flat space theory, then you want to say recover the amplitudes, which will have branch cuts. But will the correlators you study, will you be studying boundary correlators here in ADS?
Yes. So basically, you can study different things. If you are still studying like higher like amplitudes in ADS, then obviously it will have some branch cut structure. But the thing that I'm going to study is basically CFT correlators. And the analytic structure of CFT correlators, they are completely understood. Like there is no ambiguity anywhere. So they have branch cuts, but like those branch cuts are basically like branch cuts.
Okay, thank you.
Yeah. Any other question? Okay. If not, let me discuss this duality in some detail. So, okay, let me. So when I say EFT in ADS is dual to a CFT, the precise statement is the following. So there is a one-to-one correspondence between scalar EFTs in ADS in d spacetime dimension and perturbative solutions of crossing symmetry in CFT d-1. So this is a famous work by Himskirk, known as Sally. So this is basically at the level of tree-level 4-point functions. This is basically holography directly from conformal bootstrap. To discuss it in more details, let me write down an scalar effective field theory to begin with, so that I have some reference. So this is the scalar effective field theory that I'm going to study. In some sense, this is the simplest thing one can write down. So this metric is the ADS metric. So we then have the mass term. And then there can be a phi cube interaction. And then there are higher derivative interactions. Plus, there can be other fields with spin less than 2. And obviously, then there is the Einstein-Hilbert term. So this is the effective action that I'm going to look at. And I'm going to study this effective action at tree level, which can be implemented by taking mu to, just considering only the leading order term in mu. Where mu was this coupling constant. Okay, so the duality is basically very simple. It's basically the ADS-CFT correspondence. So for the field phi, there is a dual primary scalar operator O with dimension where is the CFT dimension. Then you have, so when gravity is dynamical, you have the graviton, which is dual to the CFT stress tensor, T mu nu. Then you can compute the 2-point function of the stress tensor, which has some known tensor structure over 2D times a numerical coefficient Ct, which is generally known as the central charge. And this Ct goes as 1 over G Newton. So this duality works in the limit where the central charge Ct is very, very large. So that's the largest quantity in the theory. But let me mention one more thing. So there are no in this effective field theory that I wrote down, so there are no high spin particles other than the graviton. So this can be stated as follows. So there is a gap scale in the CFT, which is large. So this is the dimension of the primary single trace operator with spin, in this case, greater than or equals to 2. So this is basically the statement that the EFT does not contain light higher spin states. Now the important point. So the effective field theory that we studied in the beginning, that did not have any dynamical gravity. So that's basically the way to think about that is the following. So in that case, we take CT to be exactly infinity, but delta gap is large but fixed. So this is the limit where there is no dynamical gravity. So in the gravity side, in the effective field theory side, what we are doing is the following. We are just taking M Planck to be infinity, and we end. So in this limit, in the safety side, the stress tensor basically decouples from the low energy spectrum. So we can just forget about the stress tensor, and we can only study the other operators. Then just from crossing symmetry in safety, one can show the following. So we started with a scalar field in ADS, which is dual to a single trace primary operator O. But crossing requires that there has to be composite operators, which are generally denoted like this, the double trace operators, which has the following form. So all these double trace operators for even L, where L is the spin, and all integer n must be present. So these double operators that are known as the double trace operators, they have spin equals to L. Dimension is given by 2 delta O plus 2n plus L. We can actually say a lot more. To do that, let's just first make the scalar EFT free. So this dimension over here, the expression that I wrote down, that's true only when the scalar EFT is exactly free. So this is for free scalar EFT. When the scalar field effective field theory is exactly free, in that case, let the 4-point correlator, let's say, in the safety side, it factorizes into 2-point correlators, because obviously there is no interaction. So that's why the dual CFT is basically a generalized free CFT. What it means is basically all endpoint correlators, they are always factorized into 2-point correlators. But it's not a free theory in the sense that this is a theory with large number of degrees of freedom, and it's strongly coupled. So in that sense, it's not a free theory, but it behaves effectively like a free theory when we study its correlators. So now when we introduce interactions. The spectrum of the dual CFT remains the same. It's basically, we have the operator O, we have the double trace operators, we have the multi-trace operators. The only difference is that the OP coefficients now receive corrections from the generalized free theory values, and also the double trace operators, so their dimensions is given by the generalized free theory values plus some anomalous dimension. So because of interaction, we have this term and this term. And at tree level, actually, we can map interactions into this anomalous dimension. And there is a very nice mapping. For example, if I add a phi to the power 4 interaction in effective field theory side, so that corresponds to my L spin 0, they becomes non-zero. But all other anomalous dimensions, they remain 0. Similarly, if I add something like phi square, box square, phi square, this gives anomalous dimension to spin 2 double trace operators. Similarly, the box 4 gives anomalous dimension to spin 4 double trace operators. So there is a very nice mapping, so on and so forth.
I mean, for L equal to 2, there is also a 6 derivative term, right? I mean, it's not just box square.
You mean something like box cube?
Yeah.
Yes.
From what I remember, there are 2 terms. Yeah.
So all these interactions, they have they are in some sense even interactions. So I have box square, box cube, 4. So what about interaction something like phi square, box cube, phi square? Since there are no double trace operator with odd spin just from symmetry, so what this interaction does is the following. It also contributes to spin 2 double trace operators. But the contribution is suppressed by RADS. So let's say this coefficient is lambda 2, this coefficient is lambda 3. The anomalous dimension is basically, the exact anomalous dimension is something like this. So lambda 2 to some power of RADS plus lambda 3 with a higher power of RADS plus epsilon, let's say. So the contribution of these odd interactions, they're always suppressed. So that already tells you that from this dual CFT analysis, you'll never be able to constrain these odd interactions because they are always suppressed.
No, that is under the assumption that so lambda 3 is dimension full. So when you write it in terms of dimensionless quantities, you're assuming that dimensionless number is order 1. So you have to still show that, right? I mean, without showing that, how can you suddenly conclude this?
It's basically it still is an order of limit issue, even if it's like it's not order 1. The order, like the order of limit that we are taking, RADS, we always take RADS to large value first. So as long as these numbers, they don't scale with our radius, and that's basically
but that's good. Yeah, but how do you know that?
So
how do you know that they don't scale with our radius?
The reason is basically like in this particular the perspective is basically we are starting with some effective filtering in flat space. So when you take the limit r radius to infinity, we have to reproduce the flat space effective action.
Okay.
So if any of this coupling constant, if they scale with r radius, they'll blow up. So they can be large, like they can be million, but they are not. They cannot scale parametrically with r radius.
Right, but I'm a little confused now. That so if you when you take the flat space limit, are you saying that this box cubed is naturally going to be suppressed?
No, like
you don't have to worry about this.
So if I look at the effective action when I take the r radius going to large limit, so obviously in the effective action that term will not drop out because it has some coefficient which does not scale with r radius. But when I look at any safety quantity such as this, the anomalous dimension, and take the r radius to large limit, then it's always contribute to subletting terms.
I see.
So it is there in the effective action, but it in some sense it's absent in the dual safety. But obviously you can study like different types of observable where this term contributes. For example, okay, I can tell you exactly where it can be important. So if I look at operators with n order 1 n and L, then basically this is suppressed. But what happens is that this the box cube interaction, it grows with a higher power of it grows with into the power some higher power. So for large enough n, then basically it can start to dominate. But I'm going to like inform my analysis. I'm always considering the low-lying spectrum, so I don't actually care about this interaction.
Okay. And are you going to talk about the flat space limit more explicitly in one of your lectures? Like how do you go from
in the third lecture, that's exactly what I'm going to do. Basically, like when you don't have dynamical gravity, flat space limit is very simple. It's basically the leading order.
That's fine. I mean, so long as you cover it, it's fine. I mean, then I can ask my question then. Yeah, fine. Okay.
So as I said, like there is a very good one-to-one mapping between the ADS interaction and the anomalous dimension.
Sorry, Sandipan, one very naive thing. So in your effective field theory D dimension, you are mapping that to CFT in D-1 dimension, right? Basically.
That's right. Yes.
But there is also one thing is that in the flat space limit, the CFT correlation function in momentum space is mapped to one higher dimensional S matrix in a quantum field theory, right? There is this also map, right? Are your effective field theory will also be related somehow that way?
Basically like what you are asking is basically some like to directly map some safety coordinator with some scattering amplitude in ADS.
Yes, not in ADS. So I take CFT amplitude, I take the flat space limit. In the all I'm doing in the flat space in the sense, let's say total, let's say a 3-point function mod P1 plus mod P2 plus mod P3 taken to 0. That will also correspond to a scattering amplitude in a one higher dimensional quantum field theory, right? That's the correspondence. So is there a connection that way to one your effective field theory as well?
Sorry, I thought these are effective field theories. 1 second. So one clarification is that these are effective field theories. Suppose you are doing 4-dimensional flat space, then you're putting it in a 4-dimensional box. So it's ADS 4. And so the CFT is going to be a CFT 3.
3, that's right.
Yeah, so that is the thing that. So when you're taking the flat space limit, it is going to be in 4 dimensions, and ADS is also going to be in 4 dimensions.
That's right. That's right. Yes.
And,
Yes.
And the CFT is going to be in 3 dimensions.
Yeah.
But
CFT is always one less.
what I was saying is that suppose you start with a CFT correlator in momentum space, let's say.
Yeah.
There is a limit which is defined as flat space limit, which is just kinematical some momentum limit.
Yeah.
That is related to QFT scattering amplitude in one higher dimension. I was asking, is there
that's the same thing?
Yeah. So obviously there is a relation because it's the same theory. Like it's not like.
Yeah, that is what it is.
But the thing is that it's basically there are two issues here. First of all, you can either try to write down some CFT correlator which relates to the amplitude exactly, and then the problem is for those CFT correlators, actually it's not possible to derive any general constraints. So because like if you can do that for those CFT correlators, then you can actually do that for the amplitude itself. So then there is no reason for you to go to ADS and study the dual CFT. So the thing that I'll try to argue is basically there are other correlators which are morally similar to the correlators that you are talking about, but these other CFT correlators, they are basically better controlled when you study conformal bootstrap.
I see. Okay.
So it would be really nice if like one can derive the, for example, I think in the Canhart et al. Paper in EFT in ADS, the paper that appeared, I guess, last month or month before that, they are trying to study CFT correlators which basically generate like flat space amplitudes. So they are basically, you have to find out exactly what kind of argument will actually give you constraints, and that you can use in to actually constrain the effective field theory. So like my goal is, I guess, more modest. It's basically once I know the dual CFT, just forget about the amplitude, just study that CFT and derive constraint in that CFT. Since I know that those CFT constraints can be translated into constraints into effective field theory, that I don't care actually whether I can map that exact CFT correlator into some amplitude. But obviously, because it's the same CFT, obviously in some way you can always do that.
I see. Okay. Thank you.
Okay, let me wrap things up. So basically, so just to give you a summary, we have some scalar EFT in ADS. So then at the tree level and at the level of 4-point correlators, just from Bootstrap, we know a precise CFT D-1 description. So which has the operator O and double trace operators and multi-trace operators. And the CFT data, that's the dimension of these operators and the OP coefficients. They are given by generalized free CFT values plus corrections, where these corrections knows about the EFT interactions. So this enables me to actually ask the dual question, which is the question that what scalar So the original question was basically what scalar EFTs can not be UV completed. So now I ask the dual question, what scalar EFTs in ADS cannot be embedded into a UV theory that is dual to a CFT obeying the usual conformal bootstrap axioms. So basically, what we did today is basically we end up with this dual question, and this is the question that we are going to study in next 2 lectures. So to give you a trailer of the next 2 lectures, so from conformal bootstrap, we are going to actually derive an infinite set of constraints on the CFT Regi correlator. So then the duality will imply an infinite set of constraints on the scalar EFT. So that's the basic setup for the next lecture. So let me stop here, and if there are any questions, I'll be happy to answer them.
Okay, thank you, Sandipan, for a very nice lecture. So what I'll do is I will stop the recording and then we can continue discussing offline.